All right, let's go ahead and get started. Before we jump back in, a couple things that I should let you know about that are coming up soon. To take place on. Yeah. Much enough. Also, so we left off last the convergence sequences. How to make those. So let's kind of rephrase here. If I ask if a sequence converges, what makes that determination? So that's does this sequence that's exactly what sequence as n gets really large, um, there is no value of there is no single value. So a couple of other ways that I want to explain this. Um, how many different terms are in the sequence? Long sequence, right? How many? Essentially, if I were to write this sequence out another way, I believe it would be negative one, one, negative one, one, indefinitely, right? So, and the reason I bring this up and I'm calling it out specifically, we did this. There's usually something involving infinity, right? So for a sequence, we don't have to have a sequence like this to exist in ways that you're going to. So if we were to graph this sequence, what would it look like? So -1, +1, -1, +1, and definitely like this, right? So would I connect these with like a smooth curve then? No, and that's kind of one of the things we have to keep in mind about sequences. Sequences are functions basically that graph it would just be this alternating. Okay, about this one. So we said that last alternating sequence diverged. Do we agree? Split, right? So let's, and here's the thing. So for a couple of these last time we were able to, like these are not continuous functions. But in the past, what we were able to do was, all right, how about I cheat and make this a function? Only I can do that this time. It's not gonna, that function is not gonna be well defined. So we can't do things like this. So we really just have to look at the sequence. So maybe it would help if we looked at a few terms in this sequence. What would the first term in the sequence be? Oh yeah. Sorry. The first index is 1, which means the first term is -1, and then 1/2. I'll rewrite this over here as -1/1. So I believe this is the pattern that kind of prevails, right? Does that give anybody? That's the that is the bottom. All is not fair to say. So because of that, this sequence does converge. So even though it alternates, it decreases, increases, alternating like in alternately. This thing converges. And if we're saying it converges, we better be able to say something specific about what it converges to. We okay with 0? So yeah, I mean, and another thing I want to bring up here. So this limit is 0. Is 0 does not belong to a sequence. Your value. So the limit is, I mean, just kind of like what you learned about limits. Function might have your answer is limit continuity theorem and squeeze theorem. So let's kind of unpack all this notation I'm throwing at you. So basically, the limit continuity theorem allows functions. So if I know I have a sequence that converges to some limit, then that limit is preserved by sequence into another. Put that sequence into another. Essentially, what this tool kind of mechanically allows to do. Know that basically no matter what value of n I have, A is always the smallest, C is always the largest, and B is always between. So basically what's going on is let's say I have three, just because it's easier for me to graph these continuously, even though I admit I'm kind of breaking rules here. So let's say I have these, let's call this right here sequence of C, and this right here sequence A. So basically A is always the smallest, C is always. If I have a sequence B that behaves in some really strange way, but that I know it will stay kind of between A and C, if I know A converges and I know C converges, I have enough. I'm trying to find this limit as n gets closer and closer to infinity. What does do we think that? So this is a good use of the continuity, the limit continuity function or function, the theorem. So what I want to do is to break this up into like basically an inner sequence and an outer sequence. Is it clear how we might break this up into two decomposed sequences? Okay, so let the inner be pi over n and let the outer be sine of n. Now let's think about these. So we have two sequences, right? Are we convinced that this right here, that sine of pi over n is equal to, what's the direction here? B of A of n. Basically, I'm going to modify this a little bit because of the kind of things that can be inputs to B. It's not really a sequence because we're going to get lots of inputs to that aren't integers. So I'm going to change my language a little bit here. I'm going to say that f of x is equal to sine of x to indicate that I don't need to put any restrictions on x. I can take whatever I want, which means I'm going to modify this to call this f of a sub n. I'm going to ask you a couple of questions here. What is the limit as n limit as n approaches infinity of a sub n? And what's the limit as x approaches infinity of f of x? Does this top limit here of the sequence A, does that have a numerator? It's going to grow down. This better go to 0. Does that function have a limit as x goes to infinity? It shouldn't. So Colin pointed out the sine function oscillates indefinitely. So this limit doesn't exist. But I don't actually care about that limit on its own. What I'm really looking at is this. What's the limit as n goes to infinity of f of pi over n? What did we just say the limit of pi over n is as we let n get really, really large? 0. So really what I'm looking at is this. I'm not trying to let the function go to infinity. I'm trying to let the function go to 0. Because that sequence does converge. But I understand, like, I think Colin asked for it right away. Like, can't we say it diverges because it's a trig relationship. So in general, yes, trig functions don't have infinite limits unless you like. But in this case, we're not letting you. The stations here. Well, if I'm asking for the convergence of a sequence, use the limit of pi over n as n. Worried about sine. So I know the limit as n goes. So as n goes to infinity, this function right here, I'm not letting x go into infinity. I'm letting x go to whatever this thing trends to. So first of all, are we okay with the way we this kind of rigorously before I talk about? We want to think about like intuitively what's happening here. So as we keep saying, the bottom line is what happens to our sequence as n gets really long. Let's break it down. And essentially it's going to be kind of saying verbally all this stuff. As n gets really large, what happens? This thing takes time. Let's see. So if this was the limit as n approaches infinity of sine of pi n. So good question. Let's even analyze this the way we did. So if we were to break this down, what's the limit as n approaches infinity of pi of n, or pi times n? Infinity, right? So that doesn't exist. So if we look at the way the theorem was presented, so basically my top two bullets are conditions I have to meet. Yeah. Let's see. What's the limit as n approaches infinity of cosine of pi over n? So let's do this first. Let's make sure the inner limit exists. What's the limit as n approaches infinity of pi over n? Still zero, right? Okay, so let's go back to the conditions of the theorem. Okay, the first bullet is limit exists, right? Zero. That's to be clear, that's the limit of like the inner sequence. Okay, second bullet. I have to have like an outer function that's continuous at in that case, then what is this new sequence converge to? This one converges to one. Because this is equal to the cosine of zero, which is equal to one. So that one converges as well. Just pull on examples there. Any other questions? Yeah. So this is another reason like sometimes you just can't make functions. N factorial is equal to, well, maybe I'll give you a concrete one first. What's 4 factorial? Right. So basically, and that's what the definition of the factorial operator is n times n minus 1 times n minus 2. Basically, multiply the product of all the numbers from n down to. But, as we were able to use L'Hopital's rule to do some other investigations last time, what happens if I do this? What is like 4.5 factorial? That's not defined. So there is no way function that involves n zero. How we doing? You understand that? What's going on there? So let's look at the first few terms in the sequence. I think this would be 1 over 1, right? And then 2 times 1 over 2 times 2. 3 times 2 times 1 over 3 times 3 times 3. that okay, or should we evaluate some of these things? Yeah, let's do that. So 1/2, 6/27, so 2/9. 6/64, so 3/32. Okay, I see a pattern emerging in the numerator, but I don't know if we're going to get one out of the denominator. 129. Yeah. Okay, so our sequence looks like this. It would be, and here's the tricky thing. Yeah, I mean, if you plug it into can we answer the question we need to answer when we talk about conversion? We need to look at it. What do we think about that? So I think that's a good assumption, but let's bring that new thing in, that new squeeze theorem. Can I at least say this? I think this was pointed out a while ago, but can we at least say this, that n factorial is less than or equal to n to the n? Does that also mean I can do this? That n factorial is bigger than negative n to the n? Okay, so here's what I'm going to do. I have a sequence that like I just can't figure analyze in a very like efficient way. So I'm going to bring in these two other sequences that I hopefully are a lot easier to think about. So you're okay with this string of inequalities right here? These three things: least, middle, and greatest, right? Does that change if I do this? Divide everything by n over n. Is that inequality still true? I basically divided all three of the branches of that thing by something positive. So if you divide by negatives, the signs all have to flip, but I divided by something that is guaranteed to be positive. Okay, so if I simplify these, what did I get? The middle one is a sub n, right? It's identical to the thing we're actually talking about. What's the one on the right? Oh, never mind, it's not what I wanted. I'm gonna make this work with the squeeze theorem, but this is not gonna work. So the punchline is that this sequence does converge to zero. I thought I could show that with the squeeze theorem, but maybe I have an example later where I can illustrate that. But the one of the big things that I wanted to take away from this is I don't think it's obvious, right? I mean, so you're going to see a lot of these things. For those cards have. It's almost impossible for this not to be true. Cards, whatever. But it's one of those things that's hard to get your hands on because it has no derivatives, so you can't really talk about its growth. But it outpaces end to the end. Oh wait, no, in this case, it didn't outpace end to the end. So yeah, it is, even though it is as fast as end is outpaced. Okay, so all I gotta do here. Time. I write out a few terms here. What's the first term in the sequence going to be? Should be R, right? Followed by what? R squared, R cubed, R to the fourth, and so on. Those are what's called a geometric sequence. And I know we talked about this, but let's get a reminder. What is a geometric? By definition, it's a geometric sequence. Variation, right? Does this thing have a common? It's so 0 is less than R, which is less than 1. So let's test that out a little bit. Let's just take a value in between those things. Let's say R is equal to a half. So then this sequence would be 1/2, 1/4, 1/8, 1/16. Does that converge? It converge to what? Yeah. Okay. So we agree that 0. Not 0. If R is 0, then what's the first term? And then 0. Does this converge? It converges in a very uninteresting way. Every single term in that sequence is 0, so it converges to 0. So that's one thing. I'm glad that came up because I want to up because I think the language. I look really dumb, but I think it'll help me make my point. What's the limit as x approaches 4 of 7? 7. Does that make sense? What about if I change that to a 2? 9, 9 pi, 14. So basically, I'm looking at something constant. Constant sequences have to converge because don't vary. So this 0 converges to 0. What about if the first term is 1? What's the second term? 1, 1. So converges to what? 1. Same reason. So I will tell you that this end, if I'm greater than 1, it's just going to blow up, right? But what if I have negative 1/2? What's the second term? 1/4, and then negative 1/8, then 1/16. Does this have a limit? 0. So because of that, I think I can have negative numbers, but how far back can I go? Negative 1. Can I include negative 1? I got one head shake. What do we think? If I have negative 1, what's the next term? I think this is the first thing we talked about today, right? So that does not have a limit. So because of that, we get some that we have a sequence, geometric sequence, as long as there's common 1 and 1, not including negative 1. We follow the logic. So some vocabulary terms that I'll throw around with sequences that it's been really hard for me not to use these terms up till now, but let's talk about the idea of a monotone sequence. So a monotone sequence is one that increases from term to term. Sequences. Okay. Sometimes you hear something else we can talk about. So, and again, I'll talk about this in a couple different ways. You have a sequence once it's bounded, there's a minimum value and a maximum value that every term is. So we said some monotones, some are not. Just looked at this geometric thing, right? Negative. So is this thing right here bounded? So we said it was not convergent, right? But is it bounded? It's bounded. It has a minimum value and a maximum value, right? And I think the rest of these are these all bounded as well. It does have a lower bound. So what's the upper bound? Well, I think it has both. If we're saying it's bounded, it has to have both. So let's talk about this. For this sequence here, what is the lower bound? Negative 1/2. What's the upper bound? Positive 1/4. So yeah, that's bounded. I think all these in fact are bounded. So let's come up with an example. What's a good R value to choose if I want one that's not bounded? Or can I? Cool, let's do 2. 2, 4, 8, 16. Is this bounded? Is it bounded below? Is it bounded above? No. So it has to have both of those conditions to be totally bounded. So why am I making such a big deal out of both? Let's talk about this. So we're working up to one more theorem, hopefully by the end of class. So this thing right here, let's answer these two questions. Is it monotone? Is it bounded? So this is the alternating sequence, the one that goes back and forth. Is it monotone? No. Is it bounded? Yes. What are the upper and lower bounds? So I can say everything in here. So bounded between negative 1 and 1. Yeah, so we said no. Why is this sequence not monotone? It does both increase and decrease. A monotone sequence, by definition, has to do exactly one of those things. So if I graph this again, negative 1, positive 1, negative 1, positive 1. So because of that, can we say that any alternating sequence fails to be monotone? If it alternates in sign, then it has to be increasing and decreasing every other. How about this thing? Is this monotone? What's the first term? 1/2. And then 3. Actually, let's just make this easier. 3/6, 3/7, 3/8, 3/9, and so on, right? Is it monotone? If you're saying yes, then let's be specific. Is it increasing or decreasing? Decrease. Is it bounded? I heard a question no and a statement yes. So let's ask, let's try to bound it. Let's try to find the bounds. Can we find an upper bound? I think if you're saying it's decreasing, then the first term better be the upper bound, right? So I think 1/2 is the upper bound. Can we talk about a lower bound? Zero lower bound. Does this thing ever achieve zero? No. So here's one thing I want to talk about with bounding is whatever you call it, don't have to actually belong to the sequence. In fact, it's kind of silly, but I could say this: oh, this sequence is bounded because it's always greater than -1 and it's always less than 10. Those are upper and lower bounds. I do not have terms in the sequence that stray above for the greatest. Okay, so this thing's bounded and monotone. Does it converge? Didn't ask you that until right now. So it only goes, and I know it can't on a certain bound. Is it monotone? 1/2, 2/5, 3/10. So if I let's talk decimals: 0.5, 0.4, 0.3, something, something. We think it's monotone. Yes. Which way? East. Is it bounded? You said it's decreasing, so the upper bound. What's it bounded below by? Yeah, I mean, I don't think it'll ever become negative or go to zero. But I can say for certain that and bounded. That guarantee. How many more of these do I have? One more. Got time. Is this thing monotone? Which way? Increasing. Is it bounded? Bounded below, we think, right? I think it's bounded below by zero. Is it bounded above? No, that's all we can say. So, no, it's not bounded. Hold that thought, but I want to talk about this last theorem here. So, the thing that a lot of you put forward, yes, is true. If I have a sequence that is bounded and monotone, it converges. So, one thing we talked about, early. This is now keep in mind that What? So the question is, have balance. Yes. All convergence sequences are bounded, but they're not always monotone. I think that's fair. So I think I asked you if you could have one that's not bounded and not monotone. Think about what this thing does. It's going to alternate and get further. All right, I'm over time. Just finish this section. We'll start series next time. Have a good weekend. So I don't know what question you're talking about. That's why I think it's so important to say, like, does X stand for basically, does X stand for the distance from the bottom of the tank, top of the tank? Whatever. As long as it doesn't really matter what you use, as long as anytime you use the symbol X. Like the height of the water. Yeah, can you pull up a question? Well, yeah, like if you have a disc, like let's say you have a pretty wide disc, it's going to take more work to get this water to the top than it is to get this. So because of that, you have to set up an integral that accounts. The distance of travel. That is the thing that the integral has to account for the. So Huck's law, just in equations, is F equals KF, right? What do the symbols stand for? What do FK next stand? Displacement. So X, in that case, I think X has to be what?